Hello guys, welcome to the fourth lecture of this course. So in the last two lectures, we talked about the um, linear momentum, the rate of change of linear momentum, the angular momentum, the rate of change of angular momentum, the weak law of action and reaction, and the strong law of action and reaction. So in this class, we will talk about the energy. So let's say we have a system of particles. So this is the coordinate we have x, y, and z. And let's say these are the particles. So a lot of particles. And this is the center of mass. So the position of the center of mass that is given by r vector. And let's say the position of ith particle. Let's say this is the ith particle. And this is the center of mass. So position of the ith particle is given by Ri. Okay. Then the position of ith particle with respect to the center of mass, let's say that is given by Ri prime. So then using the triangle law of addition of vectors, we can write that Ri is equal to R plus Ri prime. Similarly, if we derivative both sides with respect to time, we will get Vi is equal to VCOM. This is the velocity of ith particle, that is equal to velocity of the center of mass plus velocity of the ith particle with respect to center of mass, that is the V dash I. Okay. So what is the total kinetic energy of the system? The total kinetic energy is given by sum over all I and Ti. Ti is the kinetic energy of ith particle. So the Ti can be written as half mi Vi square. Okay. So this is the kinetic energy of the system. Then this half mi Vi, if we replace this Vi by this term, so this is sum over I half mi. Vi means half mi. Vi square means Vi dot Vi. Okay. So we just replace this Vi with this term. Then we will get VCOM plus Vi dash dot VCOM plus Vi dash. This will be sum over I half mi VCOM dot VCOM plus VCOM dot Vi dashed plus Vi dashed dot VCOM plus Vi dashed dot Vi dashed. Okay. These are the dot products. So then what's the value of this? Then the kinetic energy P is equal to This is just VCOM the whole square, magnitude of VCOM square, and this is constant. So that means it has no, I mean constant it has no I index in there, so it will come out of the summation, and then it will be just sum over mi, and sum over mi means capital M, that is the total mass of the system. So then this term will be with multiplied with the half factor. This will be half m VCOM square plus the next term. What about the next term? So for this next term, this VCOM, it has no I index, so it will come out of the summation, and then we are left with sum over mi vi. Okay, so this term will be like this. So half VCOM dot sum over I mi vi dashed. And what is sum over mi vi dashed? This is 0. Okay, this is already proved in the last class that this is 0. So then there will be two such term, this term and this term. So it will be 0 plus this term. What is this term? This is half sum over mi vi dash square. So this is sum over I half mi vi dash square. Then this means T is equal to half m VCOM square plus sum over I half mi vi dash square. So what's the significance of this equation? This equation says that if you want to measure the kinetic energy of the entire system, that system of particles, then first measure the kinetic energy of the center of mass. I mean, by considering that all the particles are concentrated at the center of mass, and then calculate the kinetic energy, that is half mi VCOM square, and then calculate the kinetic energy of each particle with respect to center of mass and add them all. Then you will get the total kinetic energy of the system. Okay, this is a very important relation. I mean, this is kind of similar to the case of the total angular momentum of the system. There also we calculated the angular momentum of the center of mass, and then all the particles, angular momentum of all the particles with respect to the center of mass. Now let's see what will be the work done if there is an external force acting on the system. So the work done, so let's say particle that goes from point 1 to point 2, then the work done from 1 to 2, that is given by integration from point 1 to point 2 if I dot dri sum over all I. So for each individual particle, we find the work done and we sum them. Okay, so you can sum it later. I mean, you can put the summation up before the integration. So what is Fi? Fi is the total force acting on ith particle. So that is basically the external force acting on ith particle plus sum over all j, where j not is equal to I, f of ij. This is the force due to other particles on ith particle dot dri. So this is the work done. So now let's concentrate on this term. Okay. So what is this Fi? This is the total force acting on ith particle. So then we can write Fi like Fi is mi d vi dt. Dvi dt is basically the acceleration of ith particle. So this is a second law of Newton. I mean, the force, total force acting on the ith particle is the mass of the particle times its acceleration. So we can write it like sum over I, only we are concentrating on this term. Okay. Sum over I Fi integration from point 1 to point 2 Fi dot dri, this equals to sum over I mi integration from point 1 to point 2 dvi dt dot dri. Now what is vi? Vi is dri dt. This means dri is equal to vi dt. Now if we put it here in place of dri, we will get, so dt will cancel and we will get vi dot dvi. Dot product is commutative, so we can put the dvi after vi. So what is this term? This term is sum over I half mi vi square from point 1 to point 2. So what is sum over half mi vi square? That is the kinetic energy of the entire system. So half mi vi square is the kinetic energy of the ith particle, and sum over all particle, that means this is the total kinetic energy. This is the total kinetic energy of the system. This means, and if we put the limit, then this means this is T2 minus T1. This is T2 minus T1. T2 means kinetic energy at position 2, and T1 means kinetic energy at position 1. So this work done W1 to 2, it is still the change of kinetic energy between point 2 and point 1 while we move from point 1 to point 2. It's still the change of kinetic energy. Now, okay, first of all, I'm calling it equation, let's say 1. So now concentrate on this term. Okay, so this is equation number 2, let's say. So now we are concentrating on this term. So first of all, we are concentrating on this uh, fi external term. So what about this integral? So this integral is sum over I integration from point 1 to 2 if external on ith particle dot dri. Now, if external is conservative, we have already discussed about the conservative force field. So if I external, the external force is conservative force, is a conservative force field, then we will always find a scalar function vi such that if external is conservative, we always find vi such that fi external is equal to minus divergence of vi, and this I index is basically divergence is taken with respect to this ith indexed coordinate. So this is the definition of conservative force field, and it's already discussed. Then it's already discussed in the first class. So then this term will be sum over I from point to integration from point 1 to 2 minus divergence of vi dot dri, which is basically sum over all I. This is minus of vi from point 1 to point 2, which is equal to, so this is minus sum over I vi point 1 to point 2. So this will be the first term. So let's call it equation 3. So this term will be that. And now what about this term, this fijth term? So the last term is sum over I. Let's look at this term again. Sum over I, then sum over j. So I can put the integration after that. That is not a problem. I naught is equal to j integration from point 1 to 2 f of ij dot dri. Okay, so this term. Now, if we use the strong law of action and react, strong law of action and reaction, we will get that this Fij is equal to minus of Fji. It will, strong law means it will satisfy the weak law of action and reaction, and the Fij, the forces will be in a direction that is the direction connected, the same connect the direction of the centers between the objects. So Fij will be in a direction that is the Fi. So Fij will be in a direction that is parallel to the distance between the I and jth object. So Fij will be parallel to Rij. So these two conditions are called strong law of action and reaction. So if these two laws are obeyed, then we can find a scalar function. If these two laws are obeyed, I mean, if Fij satisfies the strong law of action and reaction, and Fij is conservative, then we will always find a V, a potential, that is we call Vij, which will be dependent on only the distance between the particles, the magnitude of distance between the two particles, that is Ri minus Rj. Only the magnitude of distance between the two particles. Vij will be the function of only the distance. We'll always find Vij such that this Fij is minus divergence of Vij, which is a function of mod of Ri minus Rj. So then in the summation, we will always find, in the summation, we will always find terms like Fij dot dri plus Fji dot drj. This means Fij means minus, let's take minus common. So then this will be divergence of Vij dot dri plus divergence of Vji dot drj. So now this divergence of Vji, so this divergence is with respect to Ij. This is Ij and this is Ji. Now if we interchange them, if we just interchange the index, then we will get a minus sign in the divergence operator. But in the Vij, it is an, as we are taking the modulus, so by interchanging Ij, it will have no effect. Vij will depend only just the magnitude of distance. Okay, so there will be a minus sign due to the divergence operator if we exchange I and j. So in that case, it will be ij divergence of ij wij dot dri plus. So this term will be basically there will be a minus sign ij wij dot drj. This is basically wij dri minus drj. So this term we will write as minus of divergence ij wij dot drij. So drij means dri minus drj. This term will be full of such summations, full of such summations. So then this summation I, summation j, I not is equal to j, integration from 1 to 2, integration from 1 to 2, f of ij dot dri. This equals to sum over ij, I comma j, I not is equal to j, integration from 1 to 2, 0.1 to 2. So what is fij dri? If fij dot dri, that is minus of divergence of wij dot drij. So now here, remember, notice one thing, that we are for this each term, for each divergence ij of wij dot drij, we are taking two terms like that. Okay, so then if we are making them equal, there will be a half multiplied with them. So we are always taking two terms. So if we keep the summation, we need to divide it by 2. Otherwise, we will be taking the terms twice. So this is sum over I, j, integration from 1 to 2. So minus sign is outside, and this is half divergence of ij wij dot drij. So if we do the integration, we will get minus sum over of I, j, I not is equal to j half wij from 0.1 to 0.2. So we will call it equation 4. So from equation 4, equation 3, and equation 1. So from equation 1, W12, that is, so from equation 1, W work done from 1 to 2 is, this is T2 minus T1. Okay, from equation 2, this is T2 minus T1. And this equals to From equation 3 and 4, we will write minus sum over I Vi from point 1 to 2 minus sum over I comma j I not is equal to j Vij from point 1 to 2. So this term we can write as sum over I Vi plus sum over I comma j I not is equal to j Vij at point 2 plus sum over I Vi plus sum over I comma j I not is equal to j Vij at point 1. So now if I take T1 in this side and if I take this term in this side, we will get T2 plus sum over I Vi plus sum over I comma j I not is equal to j Vij at point 2 is equal to T1 plus sum over I Vi plus sum over I comma j I not is equal to j Vij at point 1. So let's call it equation 5. So let's look at equation 5 carefully. What do we see? If we define this term, if we define this term as the potential of the system, so if we define this term as the potential of the system, the potential energy of the system then we will see that the total energy will be conserved. Okay. So if the potential energy of the system is V equal to sum over I Vi plus half sum over I comma j I not is equal to j Vij, then we will get kinetic energy plus potential energy, that is the total mechanical energy of the system is conserved. So this is the conservation principle of total mechanical energy. This is the conservation principle of total mechanical energy. So here, what are the things that plays important role at this for this conservation principle? So one is the strong law of action and reaction. So the Fij, the internal forces should obey the strong law of action and reaction. Another thing is all the forces, I mean the internal force and the external force, both should be conservative. Only then we will get this conservation law of total mechanical energy, where the potential energy is defined like this. So the potential energy that we defined is Vi plus sum over Ij, I comma j, I comma j, I naught is equal to j, half of Vij, where Vij, so this is the potential energy, this is the potential energy due to internal forces. So this Vij, this potential energy due to internal forces is Vij. It's the function of the distance between the ith and jth particle, the magnitude of distance between them. So if Ri minus Ij mod is fixed, then sum over I comma j, half of Vij is constant. This means Fij's do no work. So Fij, the internal forces, are not doing any work. So for what kind of objects this condition is satisfied? This distance between the particles, the individual particles, these are constant, fixed. These are called the rigid body. In case of rigid body, the distance between each particle, I mean, let's say for this particle and this particle, it will always remain constant. So the potential energy due to the internal forces that are not changing, and the internal forces, they are not doing any work. Okay. So we will discuss more on rigid body in later chapters. So for today, that's all. Thank you.